We're Team Inspiration, a second-year RoboSub team consisting of middle and high schoolers. My name's Colin, I'm in 11th grade, and I'm this year's team captain. We'll be recapping our journey in 5 parts: introduction, system overview, competition strategy, development and testing, and we'll be concluding with outreach.
My name is Ashiria, I'm in 9th grade, and I'm the deputy team lead as well as on the vision and navigation sub-teams.
My name is Noah and I'm in 9th grade. I'm on the mechanical and electrical team.
My name is Ish. I'm in 9th grade and I'm in the hydrophone lead. I also worked on the electrical sub-team.
I'm Mabel, I'm in 11th grade. I'm the business and branding lead as well as part of the hydrophone sub-team.
My name is Shruti and I am a 9th grader. I am the electrical and vision lead.
I'm Behel, I'm in 9th grade and I'm the electrical and computer vision lead.
I'm Ashika, I'm in 9th grade and I'm part of the vision and electrical sub-teams.
Hey there, my name is Aditya. I finished the 11th grade and I'm the navigation and programming lead.
My name is Rishi. I was in the 9th grade and I'm the software architecture lead as well as being in the navigation sub-team.
Hi, my name is Ryan Shapur and I'm currently in 7th grade. My role is hydrophones, electrical, and testing.
We use a system engineering design process to highlight key requirements that our robot absolutely had to accomplish and kept our team focused throughout the testing period. We use a parallel rapid prototyping to allow our team to explore multiple approaches and designs in a short amount of time. We use the agile design process and shorten the build season into 1 week increments to allow our team to achieve small achievable tasks every single week. We incorporated preliminary design reviews into meetings to allow our teams to take a fresh perspective on the designs to see if we're going down the right path, and we incorporated industry professional feedback in their knowledge base to help improve our robots.
We included a forward-facing camera to see the buoys and a downward-facing camera to see the markers.
A significant addition to our sub over last year is the Doppler Velocity Log, or DVL, which is widely considered to be the crown jewel of AUV sensors, as it can accurately determine the AUV's velocity and subsequently position underwater with high accuracy. In fact, we calculated in our simulation that over a span of 100 meters, the maximum error the DVL calculates in our position is no more than 0.1 meters.
We're using the Newton Subsea Gripper from Blue Robotics as a competition-proven claw and manipulator to put on our robot.
As we're competing with 2 subs this year, we bought a pair of modems to do the inter-sub communications task. Also because it is a very interesting topic and is worth a lot of points in the competition.
This year, we wanted to challenge ourselves. We never used pneumatics in any robot system before. We're integrating that into our torpedo launcher this year.
We used prior experience from drones to better suggest materials such as a dampener to help reduce the drift in the IMU.
This year, we used an NVIDIA Jetson Nano as our main processor for navigation, as well as a Raspberry Pi for computer vision.
This season, we created a detailed power distribution diagram in order to ensure that all of the components on the robot receive an ample amount of power. We made sure that our power distribution diagram was easy to read in order to prevent confusion on the mechanical team.
Last season, our 5-volt regulator started smoking. To prevent that from happening this season, we fully heat profiled our board and identified where we need power regulators, such as heat sinks.
The kill switch design last year was inefficient and potentially dangerous to the AUV and divers, since the time delay was too large between actuation and killing of the motors.
Can you kill it?
Okay, Jim, if this thing is out. Can you hold it? Okay. You still go.
No, you had one job.
Hey guys, it's still going.
This season, we decided to pursue a better hardware switch that uses MOSFETs. We added a separate power path for thrusters and remaining electronics.
Last season, we had failed to identify that there would be magnetic interference between the components in the enclosure. This led to a faulty compass. To fix this season, we realized which components can cause interference and which ones shouldn't be interfered with. So that way we were able to use proper techniques such as shielding to help fix our drift.
We use a 80-20 aluminum extrusion for a robust design for our frame and incorporate that with 3D printed parts for complex geometries.
Now I should go over a basic review of this year's sub. First is our use of 4 hard mounting points, which will be useful during maintenance to pick up the sub, and also during the competition to pick up the sub by the crane. Next is the fact that we use basic T200 thrusters from Blue Robotics. This was competition proven because last year we used them and they worked out well with the configuration that we used.
One of our main focuses of the year was to expand the capabilities from past. In past robots, we were limited by the amount of enclosure ports that our robot had for different attachments and sensors. So this year, our team upgraded to an 8-inch diameter enclosure for a 30% increase in volume and a 60% increase in the amount of ports we had for penetrators.
And finally is the fact that with the limited sponsors, we had to move to a 2D plane subtractive manufacturing instead of additive manufacturing, which would mean that we would be using plates instead of complex 3D printed parts to mount our electronics.
We're going to be deploying 2 robots into the competition pool this year. Orange will be completing the simpler tasks, while Gray, with additional payloads such as the DVL, hydrophones, torpedoes, and grippers, will be attempting the further tasks. They will be communicating with one another with the modems.
The software for our system is split across separate processes. All the processes communicate with each other over ROS, or Robot Operating System, which is a new thing for our team this year. Several of the processes work to find the location of the AUV in the pool, both its absolute position in the pool and its relative position based on other objects in the pool. This data is then sent to the voting algorithm, which filters out incorrect localization data, and sends the correct localization data to the thruster control process. The thruster control process uses the position data to navigate the sub to the next target position by sending mavlink commands to the flight controller.
Our localization process determines the position of the robot from the key sensors on our AUV. We then feed that position into the thruster command process, which specifies where we want to go. Based off that, we will calculate the angle that our robot should point towards to be able to navigate to the position in a straight line. Once we point to the position, we then travel forward using a DVL in a tight PID loop, which means that as we approach the target position, our speed decreases proportionately so that we can reach the target position with precision and to minimize drift after traveling.
Last year, one of the shortcomings of our team was the lack of computer vision integration. So this year, we focused on getting that completed relatively earlier in the season. We decided to convert all the data given by CV, including coordinates, confidence, size, and more, into a JSON file and send it through a UDP port. From here, the navigation program could easily read the values and use them as necessary.
Last season, we were unable to integrate computer vision into our robot due to our short timeline. This season, since we integrated computer vision into our competition strategy, we were able to provide another option to the navigation team to solve missions like the gate and buoy.
Using our experience from First Robotics, we decided to use Vuforia to identify the images in this year's challenge. We started out by prototyping on an Android phone, and then concluded that it would be unreasonable to use the phone inside the enclosure, as you wouldn't be able to turn it on and off or restart it. For this reason, we ported the system onto a Raspberry Pi, where we got the same results of X, Y, Z coordinates and roll, pitch, and yaw values.
Using our knowledge from last season, we decided to use OpenCV to detect objects that were farther away with less details. We quickly identified which algorithms we would use to build off of last year's program, and we faced issues such as false positives, which we fixed by applying multiple failsafes such as size thresholding. Using machine learning was the next step in image detection after learning OpenCV. The neural network would be useful for detecting small details similar to Vuforia. We split long videos into their frames to get thousands of data points in a matter of minutes.
In our design this year, the hydrophones are placed as far away from each other as possible to help maximize their precision. We're able to use an affordable microprocessor and exploit its ADCs to sample at nearly 200 kHz at 12 bits per second. We use techniques such as the delta between the times of arrival of the sounds for each microphone to figure out where exactly the sound source is. Because this was a fairly new concept to us, we had reached out to several industry professionals across the nation to help us out.
Before COVID, our team did a lot for competitor analysis and research. We saw what worked and what didn't work for prior teams and prior seasons, and we applied those ideas into getting our past seasons of past platforms of RoboSub, orange and also blue, into competition-ready platforms for this year's season of RoboSub. We did this in parallel while we developed our newest competition platform, gray, so that we would be able to maximize the amount of time that we had in person. We pivoted after COVID-19 hit to distribute these platforms to our different members who had direct access to pools. Programmers were able then to connect in to test and get real-world results from our competition platforms from the comfort of their own homes. When the competition turned completely virtual, our team pivoted to focus on the website technical paper and video, while also kept on pursuing the completion of Gray so that we would be able to verify our simulated test results with the real deal robot.
Due to the coronavirus lockdown and the increasing difficulty of testing physically, we decided to invest our time into simulation. With the simulation, we aim to verify the capabilities of our AUV in practice. We used the simulated flight controller alongside a 3D model of a robot inside the Gazebo robot simulator. This setup let us send commands to simulate thruster control and let us run navigation experiments virtually. This setup also accounted for most of our sensors, as Gazebo gave us the means to access velocity, position data, and heading. However, our localization system also depends on a camera and hydrophones, something that a virtual robot does not have. Because of this, we wrote programs to send over fake computer vision and hydrophone data to the navigation program. We then observed the behavior of the navigation program in response to the fake data that we were sending over to make sure that the navigation program was working correctly.
Because last season we had a lot of struggle getting precise readings out of our compass, we took it upon ourselves this season to test our flight controller along several others to see which one gave us the best readings. That way we can use the best one for our purposes. However, we had abandoned this pursuit as the competition shifted to a virtual one.
We tested our hydrophones in an at-home setup similar to the configuration it would be on our RoboSub. This enabled to test out our code quickly and efficiently, as well as allowed us to iterate our design quickly and easily. After we settled on a design, we tested our hydrophone setup in our teammates' pool to see if it would pick up the direction a sound came from accurately, and if it could pick up sounds within the competition frequency range.
Collaborating with others around the world is vital to our team's success.
This year we had the outreach opportunity to work with UCSD students to design a custom printed circuit board that would act as our power distribution module. We gave them the specifications and they were able to design it and fabricate it for us. We plan to make this open source by posting it on our website.
In the past year, we traveled to Benin, West Africa, and Paraguay in South America to be able to host robotics competitions in order to engage the community in STEM. But even more importantly, we've worked with university and government officials to be able to increase the access to STEM education in their schools, to be able to improve the quality of education and STEM in the region.
We are working with a school in Indonesia to create video tutorials to help their students become more active learners and to prepare them for the industries of the future. This is also to help integrate STEM curriculum as a resource as the teachers move to an online education platform for the coming year. We use our 3D printing capabilities to print face shields to show our support of and appreciation for the healthcare workers combating the coronavirus.
We are also working with a local company in San Diego named Porpoise Robotics. We are trying to create an affordable ROV for STEM purposes, which they can help to teach underwater robotics throughout schools in California.
We learned a lot this season. We hope that you'll take a look at our website and social media to hear and read more about the design process and lessons learned about all the mechanisms that were covered in this video.
See you in 2021.